Let's talk a little bit about the program development cycle. It's over here on the left. Now, I took this from the textbook I have. I think I have an older edition than you guys do. But somewhere in Chapter 1, they talk about the program development cycle, and it says something like this. Maybe it's slightly different in the edition you have. 1, understand the problem. 2, plan the logic, and so on. So I'd like to talk through these 7 ideas just generally and say what's going on. So first of all, where does this come from? Back in the 60s, they had what sometimes is called the software crash. And what that means is that in the early 60s, all the computers had just been invented. They were huge things, mainframes that took up a whole basement of a building and so on, and only the biggest companies had them. There were definitely no personal computers, or certainly not any smartphones or anything like that. So the computers took up, the whole ground floor of a large building. Banks had them, universities had them, the military had them, not many other places. And they were programmed in some fairly rudimentary ways. The programmers themselves tended to be engineers who'd actually built the computers, so they knew all the ins and outs of everything. And they had to write the programs so they were as efficient as possible. So they used all sorts of clever tricks to reuse the same memory in the computer and overwrite one part of the program with another and things like that, just to keep everything condensed. And they used, as I said, their engineering knowledge of how the computers had actually been built. And then in the middle 60s or so, all those early computers, all the computer programmers who'd been the actual engineers who built the program, the computers, moved on to other positions, and companies started finding that they needed to update the programs they had to deal with new software or new situations or to fix bugs that had been discovered. And they started finding that when the newer programmers came along, they had no idea how the old programs worked. And it became such a difficulty to fix the old programs that in many, many cases, it was more efficient and cheaper to just scrap the whole thing and program everything again from the beginning. And around that time, that of course happened over a period of several years, but it's called the software crash, as though it happened in a day, because all of a sudden, all these programs we'd written weren't really maintainable. They weren't updatable. It was too complicated to do any of that with them. And so around that time, people started deciding that we needed to do something about this, and the field of software engineering was born. And software engineering looks at the process of writing programs and tries to figure out what are the things that make it efficient or less efficient, and how can we make it as efficient as possible. And that led to several things. It led to the development of a whole series of new programming languages. It led to the development of a new way to teach programming, which is still reflected today in the things that I will teach you. It led also to the field of to the understanding, I guess, of the program development cycle. And so the first thing I want you to notice here is the program development cycle means more than writing the program. If you were to call it writing, just think about it as writing the program, it would be steps 2 and 3 here. Plan the logic and code the program. And maybe 4, use software to translate the program into machine language. It also includes testing the program, also putting it into production, and finally 7, maintaining it. And 1 at the beginning, understanding it. The point here is that the idea is once you create a program, you need to think not just about how long did it take to write it, you need to think about how long will it last before you have to junk it and start over, and how quick will that be. So the idea is if somebody writes a program in a month and it runs very efficiently, but you have to rewrite the whole thing the next week or the next year, that's not nearly as efficient as somebody who writes the same program in a month and a half, but it lasts for 10 years. So the first thing was to recognize that when you look at software, you need to not just ask how does the first version work and how quickly do you get it working. You need to ask, will it be easy to maintain, easy to modify, easy to make changes to in the future without having to redo the whole thing. And so there's a difference between a program that works and a program that works in a way that's well designed. And well-designed software is modifiable. Well-designed software can be updated quickly and easily without having to redo everything. And that depends on how you write it in the first place, how you design it in the first place. Several years ago, like 20 years ago, we were writing objectives for each department. And one of the objectives for the computer programming department was that students learn to write well-designed programs that work. And the dean at that point in charge of it objected to that it was redundant. He said, you don't need to say well-designed programs that work, just say write programs that work. And I kept trying to tell him, no, a program that works may still be poorly designed, because well-designed means that it has to also be modifiable for the future. And I don't know if he ever got it or not, but we've moved way past that in the last 20 years. But that's the point. Being a working program is not nearly enough. You need to be have a working program that's easy to modify, easy to design. And the key to that is to have what's known as good design. And so part of software engineering is to understand what makes a program well designed. Part of software engineering is, as I said, it's reflected the way we teach programming. These days, when we teach programming classes, we try to teach people to use good design. One of the goals that I have in teaching this class is to teach you how to produce algorithms that are well designed. But all that comes from this idea that the program development is a cycle that goes from writing the program all the way through maintaining it through for however long that takes. And it is a cycle, not a straight line. When you get to 7, maintain the program, guess what you have to do to maintain it? You have to go back and make changes, which means you have to redo steps 1, 2, 3, 4, 5, 6, at least in portions of the program. So it really does go around and around in a circle. Now, what I'd like to do is talk about each of these 7 steps a little bit. Number 1, understand the problem. Sounds like something teachers just say, but it actually is surprisingly important for programs. It's very, very easy to write a program and discover after you've written it that you didn't understand what you were supposed to do in the first place. And that's because when people ask for a computer program to be written, they're not programmers usually, and so they don't know exactly how to ask for it, and what they ask for isn't necessarily what they needed. And so sometimes there's whole jobs there's whole people who have jobs whose their whole responsibility is to be the go-between between the person who requests the software and the person who writes the software, and to figure out specifically what specifications there are. This is like having a blueprint in a way before you build a building, or not even a blueprint, but just a list of sort of a contract that says here's what we're going to provide. When I was just out of high school, my dad, who was a nephrologist, a kidney doctor, hired me for the summer to program some things on on the personal computer they had in their office to try to help him keep sort of a database of customers. This was way earlier than any of this stuff would have been easily available. And he figured he could pay me some money and help support me for college, and it'd be tax deductible and everything else too. So I was capable of programming, not super well, but I'd learned enough to do some. But the problem was I wrote he told me everything he needed, I thought, and I wrote the whole program, and I took it to him, and I said, well, here's how it works. And he says, well, what happens if I type in this customer name here? How do I get to that? And I said, oh, you want me to do that? He said, well, yeah, that was the point. So I went back and rewrote it and had it do that, and came back and he typed something else and said, but what if I do this? And I was like, oh, you want me to do that? It's the whole summer I kept rewriting the program over and over and over, and it never was what he wanted. And it's not that he was being picky, or it's not that I wasn't listening. It's that it turns out to be difficult to specify what you want in a program if you're a non-programmer talking to a programmer. And neither of us had learned the ability to sort of work through that. So this kind of thing happens in a smaller scale a lot of the time. People write programs and only later they realize they didn't understand the problem thoroughly. Sometimes nobody even really understands the problem until it gets worked out. Another time I was working many, many years ago, I had some students come back to me after they graduated, and they had somebody hire them to write a fast food program. What he wanted them to do was write a program to schedule workers at a fast food restaurant. And so I helped them for about a year to try to work this out. And one of the things we did was we sat down and we sort of mapped out everything this program was supposed to do. And I'll talk more about that a little bit later on, maybe. But it was supposed to schedule workers for a fast food restaurant. So there was a bunch of information it already had available to it. It had available how many workers there were. It had available what hours they were available to work. It had available what skills they had. And it was supposed to make sure that there was somebody at the grill who could do that, and somebody who was capable of closing if it was closing time, and so on. And it's supposed to make sure that it had enough workers there. And one of the things it was supposed to do was decide how many workers we needed to have, and that got complicated because we tried to estimate that based on what time of season, what season it was. Like in the winter, that didn't need as many workers maybe as in the summer. What time of day it was, like around dinner time, we needed a whole lot more workers than not. We did all sorts of other things for that. There were a lot of different things we did. So eventually, we ended up with a program that would schedule a worker for an hour. It would schedule workers an hour at a time. It'd take the first hour, like 8 o'clock on Monday morning, and schedule a worker for then, and then 9 o'clock, and schedule enough workers for them to fill the hour up, and then 9 o'clock it would schedule workers, and then 10, and it would keep going. And if it got to the end of the week, and it needed a worker, and the worker who was available had already worked 40 hours a week, it would go back and unschedule him from earlier, so it would have room to schedule him here. And it just kept trying until it got to a solution. And our idea was when it finally gets to something where we have the right number of people scheduled every hour, and they have the right skills that we need, and they're scheduled for the right numbers of hours in the week that they're supposed to be scheduled for, we should have a working program. And we wrote the whole program to do that, thinking we understood the problem, and we produced the first test answer, and here's what it did. It took an employee, say named Smith, and it scheduled him from 8 to 9 on Monday morning, and then from 10 to 11, and then from 12 to 1, and then from 2 to 3. He was scheduled 4 separate hours on Monday, but he had hour breaks in between each of those hours. And we said, what kind of schedule is this? And looked at each other and realized this is a totally useless schedule. We had forgotten to tell the program, when you schedule these things, make sure that people are scheduled in a contiguous block, that they keep working as long as they can in a day before they take a break, within limits. So that was something that was perfectly obvious once we asked about it, but nobody had thought about it before then. So we didn't completely understand the problem. So one of the things I want you to notice is that when you're writing a program, you need to think carefully about what it is you really want. And even when you do that, you may discover halfway through the development of the program that there's something you misunderstood about it. Oh, I forgot to think about what happened if that number was negative. Or I forgot what would happen if the file was empty. Or I forgot what would happen if two people both had equally high values and I didn't know which was the highest. Or there's a lot of places where I'll ask you to do something and you need to think ahead about what could go wrong with the problem. What kinds of boundary cases are there that you haven't thought about? Understanding the problem is a tricky thing. Now, in our class, part of understanding the problem is very straightforward. It just means that I will give you programs to do on the tests or in the assignments. And part of what you'll have to do is make sure that you read carefully and see what really is being asked for. So that's part of what it is for us. Plan the logic and code the program. I'm going to think about those two together. Plan the logic is what I talked about last time as being algorithm design. It means that you're deciding what is the series of steps you want the program to go through to do to solve things. So in our case, the series of steps were, for example, we wanted it to pick a person. We wanted to look at the hour, identify how many people were supposed to work that hour, identify what skills we needed, look through the employees. For each employee, ask if he had that skill, and ask if he had hours left he could still work. And if he did, schedule him, and then repeat. And if we got to a place where there were no employees with those skills left, we were supposed to go back to the previous hour, find some way to free somebody up so they would be able to work this hour, and so on. So there was a long, complicated process. Now notice I can explain that all to you and never use C++. I can just explain it to you in English words. On the other hand, notice I didn't really explain it to you very much. To really explain it would take pages and pages and pages to work that out carefully. If you formalize that and make a sequence out of it and put the steps in order so that you have step 1, step 2, step 3, step 4, never using a lick of C++, you end up with an algorithm for the program, which we'll talk about a lot in a couple of videos from now. But an algorithm is essentially the logic for the program step by step in sequence. And it doesn't have to use a particular programming language at all. So a lot of times the hard part of programming is that. It's figuring out what you want the computer to do in the first place. What are the steps you want it to go through? And exactly what order do they need to be in? What does it need to do first? What does it need to do second? What does it need to do third? When does it need to loop? When does it need to check for things being out of range or anything else? That's the planning, the logic. And that's the trickiest and maybe the most fun part of programming. After that comes the coding the program. And often what you do is you take the logic that you've already got written down in some way, or at least you have it clear in your head, and then you just translate it into the language you're using. So if I'm writing my program in C++, I use C++ statements to do the very thing I was talking about. But if I'm writing my program in Python, I use Python statements to do the same thing. So that's the step called coding the program. Now those are separated. People don't always do them completely separately, but they sometimes do. There are some companies, several years ago, a friend I had worked at IBM, and at least at that point, if you programmed at IBM, you were expected to plan the logic before you ever started coding. And you were supposed to produce pages and pages of documentation, usually in the form of flowcharts, saying here are the things our program is going to do. And then you would write it up in coded form after that. And they wouldn't let you start coding until you had documented the plan. So that's not always the way it works today. But even if you don't write it down in a flowchart or in pseudocode or something, you should at least be really, really clear in your mind what the plan is. The biggest way to guarantee that your programs won't work is to sit down and just start sort of typing in what you think will be there without having a very, very specific order in which you want to walk through things. You sort of need to get the plan done first. Okay, once you code the program, you put it into some programming language like C++ or Python or whatever else, and that leads to step 4. Now, step 4 says in the book that I have, use software, a compiler or interpreter, to translate the program into machine language. Usually, people would use a single phrase for that, much shorter than that. They would say, compile the program. The reason the book said it a lot longer is because you don't know what compiling the program means, probably. So they had to spell it all out. I'm going to talk about compiling the program in just a few minutes in my next video. And after that, we're not going to worry too much about it. But basically, the idea is this. When you write a program in a certain programming language, say C++, the computer it's not actually built to understand C++. So you have to have another program take your C++ program and translate it into a language that the machine can understand. Machines usually run something known as machine language. Actually, there's a different machine language for every different brand of computer, every different brand of chip or kind of chip. But each computer has its own, each kind of computer has its own machine language. You don't write your programs in machine language, you write your program in something more user-friendly like C++, and then you have an automatic program translation by your program into a machine language program. And that translation happens by software itself. You don't do it as a human. That translation is called compilation or interpretation, compiling or interpreting. There's a slight difference between compiling and interpreting. In our case with C++, we compile, so I'll just use compiling. But realize it could be interpreted as well. They're very similar for the purposes of what we're talking about. Okay, so this is hardly worth being a step in the software cycle. All you have to do is just hit a button and say compile, and that will usually do it. They only threw it in here because they knew you might not realize that happens. For really long programs, you can sometimes have to compile and wait a half hour for everything to compile. But for our programs, it'll be hitting a button and waiting 30 seconds, or maybe even 2 seconds. I'll show you that whole process later on. Anyway, moving on then we get to testing the program. So programs nearly always have bugs that people didn't realize that they had. And the key to getting around those is to have really good software testing. I won't say much about that here, except to say that, again, there are whole courses about software testing. You can take upper-level courses that are all about software testing because it can get very complicated. You can't test a program by just running it once because programs, remember, when you run them, can run under a variety of circumstances. The input might change from day to day. And to test it, you really want to catch all the things that could go wrong. Not only that, programs run in the background of other programs running. So a lot of times the bugs you run into in the programs you buy, you think, well, didn't they test the program? Well, they did, but they didn't test it with the particular set of programs running that you have on your computer. And what they didn't know was that if their program was running at the same time as you happen to be running a certain CD player and happen to be using a certain web browser and happen to be running a certain spreadsheet in the background, all those things turns out they combine and there's something wrong with the program and their program will crash. Well, they're not going to find that easily by testing because they won't think to try it with all those different options. So testing the program thoroughly is a very difficult thing, and it takes a lot of work. And the best you can do is just the best you can do. There will still almost always be some bugs. But boy, it makes a difference if you can test it most of the way. There's kind of an art to that. In our class, what this simply means, since you don't have an actual compiler, so you can't run these on the computer, simply means that I expect you to think about all the simple ways that a program could go wrong. What happens if the user types in the wrong stuff? What happens if they give you the kind of input you don't expect? So I will ask you to think about those kinds of things a lot as you turn things in. I'll give you rules. For this one, you don't have to worry about if they type this in. For this one, you do need to think about this. But some things I won't mention, you're just supposed to think about it yourself. Definitely don't just turn into programming having tests. Sometimes I'll give you example data in the program assignment. I'll tell you, for example, if they enter this, it should produce this. Just because your program works for that set of data doesn't mean that it will work for everything. And when I grade it, I'll test it on other data. So you need to make sure that you've thought about how your program works for all the different data. Then you put the program into production, you sell it, you do it, you figure out however you're going to sell it and market it and everything else. And finally, there's maintaining the program. Now, one of the things that is important to point out is if something goes wrong along the process, you may have to go right back to way back to the beginning to work it all the way through. If you're testing the program and you find a bug, you might have to go back to re-understanding the problem. Wait a minute, where did that bug come from? Did we misunderstand the problem in the first place? Do we need to rework the logic? Then do we need to recode it? And now we recompile it and move on. Okay, so that's the program development cycle. Just be on the alert as we walk through our smallest programs during this semester. Ours are little tiny ones compared to the stuff that's usually written out there. You will notice some of these things sort of being applicable. But in the meantime, I wanted you to sort of understand the theory of that. What I'm going to do in my next video is show you this issue of compiling a program into machine language and talk a little bit about how that works. And after that, we'll start talking about algorithms more specifically. For now, it's number 2, plan the logic, that most of this class is about.